Today we're going to talk about adiabatic flame temperature in a steady state system. So what we've got here is our system setup where we're going to have an air and a fuel coming into the system, and that system is going to produce a flame. So you can see here we have our flame output. We're going to say that the temperature in Tn of our system is going to be equal to 298 Kelvin. 298 degrees Kelvin. And the first step, what we're going to want to do today is set up our energy flow into and out of the system. And because this is adiabatic, what we're going to be doing is, instead of our traditional formula, what we're going to be left with is simply our enthalpy into the system. Hn is going to be equal to H out. Normally that's set up as a equation that deals with potential and kinetic energies, but in this system that is all negligible. So we're going to be left with Hn is equal to H out. Because we're looking at this as a changing system, we're going to have to take into account the integration change from the flame. So what we're going to do is we're going to set this up and we're going to write it as the heat of formation, taking into account this formula, the heat of formation of the temperature out. Let's call that T, and we'll write up here, T equals T out. Heat of formation of T is equal to the heat of formation at 298 plus the integral of our changing temperature. So we're going to go from 298 to T. And this will take into account our specific heat of T. And this isn't very representative, so I'm just going to say this is due to the change in this final temperature. This is Cp. All right, so next what we're going to be doing for our formula is using this equation here, equation 107 from KimCAD. You can see here you have A and B relating to C and T, and then E and T separately. So what we're going to do is we're going to solve each of these individual components using Wolfram alpha. So I have first input here the C of T portion, and the equation that it yields is correct. The C, COTH, C over T plus constant, but this will all be multiplied by B. And then similarly, we can now solve for the other side, the E and T portion, simply by changing this from sine to cosine, and we're going to change our variables C to E. And you can see from that, this is the second equation that we are going to be using, and we will be multiplying this by constant D. All right, so next what we're going to want to do is begin to perform our stoichiometry. So what I've done is I've set up here the chemical reaction for our system, and what we have is with CH4 methane, C2H6 ethane, and C3H8 propane. So for each of these we have a stoichiometry balance set up. And basically we're just going to have each of these different fuels reacting with air. So in order to account for air, what we're going to do is just consider the oxygen and the nitrogen components. And we're going to define that as 79% nitrogen and 21% oxygen. So if we want to go ahead and set up here for the methane, we can first look at our carbons. We can see that we have one carbon on each side, so we can assign a 1 both sides here. Next, I'm looking at hydrogen. So we have 4 hydrogen on this side and only two on this side. So we're going to need at least 2 water, 2 H2O. And then I can see we have 2 plus 2 is 4 oxygens and only 2 oxygens on this side. So we're going to need to have 2 of those. So what you can see here is a balanced equation other than accounting for nitrogen. And in order to account for nitrogen, what we're going to do is multiply by this ratio. So we're going to have 2 on each of these. And then we're just going to multiply by 79 over 21. And then same on this side. Well, I wrote that over oxygen. That was meant for nitrogen. All right, so what you can see here is a completed stoichiometry for the methane. Now we're going to do this for the same thing again for ethane. So we're going to first look at our carbons again. We see we have 2 of them on this side and only 1 of them on this side. So we're going to say 1 carbon here, and we're going to go for 2 of these. That is next going to leave us with, we can look at our hydrogens. We have 6 hydrogens and on this side and 2 on this side. So we're going to go with 3 H2O. And finally, that leaves us with our oxygen component. So if we balance this, this would give us 7 over 4 for the O2 component. And we're going to say the same thing for nitrogen again. So we're just going to multiply by the same ratio. So we're going to have 7 over 4, 7 over 4. And we're going to multiply this by 79 over 21. 79 over 21. Do the same thing for propane. So we're going to count our carbons one more time. So we're going to say we have 1 of these. And then we're going to look over here for our CO2. So in order to balance, we need 3 carbon to get 3 on this side. And now we can look at our hydrogen. We have 8 of them over here and only 2 of them here. So we need a 4 H2O. And now we can count our oxygen. So we're going to have, on this side, we only have the 2 oxygens. And over here, we have 6 plus 4, so 10. So we're going to need 5 of the O2. So, and then once again, we're going to do the same ratio for the nitrogen. So we're going to say we have 5 moles of nitrogen here, and we're going to multiply this by 7 over 4, 79 over 21. And you can see here we have a balanced stoichiometric equation for methane, ethane, and propane. Because in this equation, we are dealing with not pure oxygen as our air. We are adding a nitrogen component, which is actually the most abundant component of this air. Our expected T out is going to be much less than what we actually expected. There's still going to be an increase between T in and T out, but because the nitrogen component also will need to be heated in this process, there's going to be a large energy loss due to specifically heating that nitrogen. Okay, so now what we're going to do is we're going to code in the equations and see if we can solve for our system. So what I've done here is I've opened Colab and I've imported a little bit of code already. So what I have is this clone bringing in a set of kin tools, and you can see here this is an example of one of those files, and it provides a bunch of ethane properties. So we're going to take all of our constants from these files here. And I've established into our vector this isn't right. Yeah, okay. Yeah, I've set this P as the properties for all of the different chemicals that we're going to be using today. So we have methane, ethane, propane, oxygen, nitrogen, carbon dioxide, and water. So now we're going to actually start solving for it. So we're going to first import all of the different, solve for the number of moles. So first what we're going to do is establish all of the, establish the stoichiometry equations that we previously solved for. So we're going to say fuel is equal to, let's set this up as, I believe it was 1 and 3 for our first one. For methane, for ethane, we got 2 and 6. And for our propane, we got 3 and 5. I'm sorry, this was 3 and 8. Next, we're going to solve for, in order to solve for the number of moles, we're going to, oops. The actual number of moles, so we're going to have 10, 1.5, 1.0. And we're going to want to set this to an array. So we're going to say this is equal to np dot array with this. Now we should be good. So now what we're going to want to do is solve for our number of moles of carbon and number of moles for hydrogen. So we're going to say NC, comma, NH is equal to our fuel underscore S at our fuel. Cool. So next what we're going to want to do is solve for our number of moles for CO2 and CO2. Let's make that capital O. Is equal to, in this case, it's always going to be equal to our number of moles of carbon, so NC. And we're also going to want to solve for the number of moles of water, then H2O. That's going to be equal to our number of moles of hydrogen, NH. I'm going to change this here, NH. And this is just going to be NH over 2. All right, so far so good. Next, what we're going to want to do is solve for our number of moles of O2. So we have NO2. And this is going to be equal to the sum, actually, of our number of moles of water, NH2O, plus our number of moles of carbon, so NC. And this is going to be over 2. Because it's O2. Didn't like that. NH2O. put a 0? I think I did. All right, so next what we're going to do now is solve for the number of moles of N2, which is equal to the ratio of air that is composed of nitrogen and oxygen. So we have 79% oxygen divided by, 79% nitrogen divided by 21% oxygen. And we're going to multiply this quantity by the number of moles of hydrogen. Sorry, we're going to multiply this by the number of moles of oxygen, NO2. Now that that is working, what we're going to do is set up our N equation. So we're going to say NN is equal to NP dot concatenate fuel underscore S, and then NP dot array, and we're going to bring in NO2 and N. And we are going to set those equal to 0. So now we're going to want to solve for the number of moles exiting the system. So we're going to say N out is equal to almost the exact same thing. NP dot concatenate, except now instead of using fuel, we can go ahead and state, because the fuel's already spent, we're just going to enter this as all zeros. So in order to do that, we're going to say NP dot zeros like, and then fuel underscore S. Okay, that looks good. See if I made any errors, and none so far. And we're going to edit this still because now that the fuel has been spent, we no longer have any oxygen in the system, so we're going to set that equal to 0.0, and our products are going to be defined by our equations that we defined above. So we're going to have NC capital O2 and N of H2O. Okay, and we're still looking good. Okay, so next we're going to want to bring in the formula that we previously solved for using Wolfram alpha. So we're going to say, we're going to define our function, define as delta H with respect to P, and we're going to return, we're going to want to return the actual formulas that we derived. Okay, so what I've done here now is import the combined formulas that we derived while taking in through the use of our toolkit, the relevant information that we were looking for each of these coefficients. So it will be able to provide us based on the chemical that we are choosing, what each of these coefficients would be. And then our final formula, we are dividing by 1,000. Because this is in kilomoles, we are dividing by 1,000 in order to solve for the number of moles. So you can see here this formula appears to be good, and we're going to move forward. So now we're going to define our functions for specific heat. So we're going to say defining H for our ideal gas is going to be, we are going to define it as NP dot dot, solving for product and of two arrays. We're going to find that as N and HF, and we are going to add to that NP dot dot again, N and our equation here, minus our change at 298. And finally, now what we're going to do is define our energy balance. So define energy balance, and we're going to bring in a vector v, and we're going to return here. And we're actually going to want to set this t at our vector is equal to 0. Sorry. T is equal to, and we're going to bring in the equation that we just wrote, H. We're going to bring that in as N, the number of moles, the number of moles into the system, so N in, and we're going to find T, our temperature, as 298. And that looks good, so now we're going to subtract by H, same thing, except now we're going to define it as our number of moles out and T out, which is simply T. So now we're going to use our root solver. So we're going to say root, and the function we're going to want to use is here, our energy balance. So en underscore val, and we need to set our initial guess. So we're going to say 298. Okay, no, that's strange. We're going to remove these. All right, let's run all. And you can see here that our solution converged. So we are good. Next, I realized from the help of my professor that this is not correctly set up and actually needs to be included in here inside of the parenthesis. So doing that will give us our final answer. All right. And you can see here we are given our final temperature of 2,181 degrees and our system converged. All right, thanks for watching.